Hey everyone, so this is the start of chapter 6. In this section, we're going to be talking about radicals and exponents. The very beginning here, we are going to do a little refresher on things that you learned in middle school about how to classify real numbers. So that's what this first page is talking about. So let's talk about different types of numbers we have. The first types of real numbers are real numbers, which sounds crazy because, like, are there fake numbers out there? Real numbers are the set of all positive and negative numbers. That's what makes them real numbers. Positive and negative numbers are real numbers. Imaginary numbers are those fake numbers. That's why we have to say we've got real numbers and fake ones. The fake ones are the imaginary numbers. And that means there's multiples of an imaginary unit. Thankfully, guys, we do not need to stress about imaginary numbers because we will talk about them in Algebra 2 next year. The next set of real numbers is rational numbers. These numbers are numbers that can be turned into fractions. So real numbers are whole numbers. Rational numbers can be fractions. Irrational are non-repeating decimals. So they're not repeating decimals. Integers are positive and negative whole numbers. And whole numbers are all natural, which are our counting numbers, including 0. So where and how do all of these numbers fit into each other? So we kind of break it down with this nice little visual here. Our natural numbers, those are our only positive numbers. So, for example, that could be like 1 or 2 or 3. So that's just, for example, Pennsylvania. That's just one state. Then we can take it a step further and we can say we've got whole numbers. So remember, whole numbers now include 0. So whole numbers are 0, 1, 2, 3, and so on. So we're getting a little bit more encompassing. So instead of just looking at Pennsylvania, now we're looking at the whole United States. Okay, and then the next step, we can take it even further to integers. Integers include our negative numbers. So now we can look at numbers. Oh, sorry guys, the screen got weird. We can look at -3, -2, -1, 0, 1, 2, 3. Those are integers, positive, negative, and 0. And now you can look at the whole map here. We were looking at all of North America. Natural numbers are within there. We're just looking at a greater picture. The next step are rational numbers. Rational numbers are our fractions. So we've got 1/2 or -2/3 or 1.5 or 2.33, and that could be the whole Earth. And then crazy, those irrational numbers are on Mars. Those are like square roots, square root of 5. Pi is irrational, those numbers. Okay, so this is kind of just a visual. You learned about this last year, which is why we're not going too deep into it right now. I just wanted to do a quick little review before we started learning new things in chapter 6. Let's classify some numbers. So let's use what we know and about the definitions of natural numbers, whole numbers, integers, and rational numbers. And we can practice classifying these numbers. So -12, think about that, it's a negative number. That means it's going to be an integer. Okay, 0, the first part 0 pops up is in whole numbers. It's a whole number. A half, once we start to get into fractions, that's when we're in the rational number category. -2/3, again, we have a fraction, that's a rational number. 1.5, a decimal, we've got a rational number. 2.33, we've got a rational number. a whole number 1, that's going to start, the first time that can go is in a natural number. It's all of the above, right? 1 is natural, whole, it's an integer and a rational number. But the first place it comes up is a natural number. And square root of 5, that is an irrational number. Okay? So questions for us just to think about. Are integers also rational numbers? So are integers rational numbers? So look here, 1, 2, 3, we could also place them down here, 1, 2, 3. So we can say yes. Are integers also irrational numbers? Well, that's no, it's a completely different category. Look, they're on Mars. Okay, they're doing something completely different. So we can say no. Irrational numbers, remember our definition is non-repeating. So these decimals do not repeat. It's kind of like, think about pi. The decimal for pi is 3.14159, so on. It doesn't repeat. So integers are whole numbers. Irrational numbers, are irrational numbers also real numbers? We can say yes. They're everything, this whole box here represents a real number. Except those imaginary numbers, that's a fake number. What is the difference between integers and whole numbers? Well, let's check this out. What's the difference between integers and whole numbers? Look at our list. Whole numbers, I've got 0, 1, 2, 3, and so on. Integers, I've got -3, -2, -1, 0, 1, 2, 3. What's the difference between these two? We've got negatives are the difference between whole numbers and integers. And what is the only number that is a whole number but is not a natural number? Again, guys, check out our list. Here's a natural number. Here's our whole numbers. What's the only number that's different in those lists? Is a 0. Okay. Little review on how to classify numbers. Now we can dive into section 6.1. 6.1, we are learning all about square roots. Perfect properties of square roots. So remember the square root symbol? Looks like this, and I'll just put square root of x because we can take the square root of anything. And let's talk about some vocabulary. So what's a perfect square? Those are super important. A perfect square is a number that results from multiplying an integer by itself. Okay, you guys know these, right? So 4 is a perfect square because 2 times 2 gives me 4. 3 times 3, look, a number by itself. That's what makes it a perfect square. 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36. And let's list some more. 7 times 7 is 49. We should know all of these, by the way, guys. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. 11 times 11 is 121. 12 times 12 is 144. We should really know all of those. Okay, you guys got it. All good. Then we can talk about a perfect cube. So we've got perfect squares and perfect cubes. So, and we can kind of really understand this just by looking at the hints of the names of these vocab words. Squares is when we just take one number and multiply it by itself. So look, squares, think about x squared, the exponent is a 2. We multiply these numbers twice, right? 3 times 3. A perfect cube is 3 times. So we're taking a number that results from multiplying an integer by itself 3 times. So 1 is a perfect cube because 1 times 1 times 1, 3 times. Perfect cube is 1. 8 will be 2 times 2 times 2 is 8. 27 is 3 times 3 times 3. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. Those are what we call perfect cubes. So what we're calling this symbol, because it can change, I know the section title is properties of square roots. That symbol that I showed you at the very top of this page is a radical. So that's what we really call that symbol. It's a radical. It's the inverse operation of exponents. They are used to undo the repeated multiplication of exponents. So when we talk about inverse operations, you know, addition and subtraction, inverses, multiplication, division, inverses. A radical and an exponent are inverses of each other. And I can give you an example. If we do the square root of 81, you know the square root of 81, that's 9. And I can go the other way around. If I do 9 squared, I'm going to get 81. So I've got a radical and a square. The exponent are inverses. Let's talk about some more vocab. When we look at a radical, we can have a number, a tiny number, right, sitting up there in the radical. That's going to be we're going to call that our index. And that number can be anything. That's why it's a variable. If we don't see a number there, we know it's a square root. If we see a number there, it could be the cubed root if it was a 3, or the fourth root if it was a 4. We've got our radical symbol, and then this number under the radical is called the base number. So we can go ahead and label those parts of this notation. And now we've got some more vocab. I apologize, this is such a heavy vocab section when we start off, but you're doing great. Let's see, square root. So there's that square root symbol. Notice there's no index. We just assume it's a 2. It's used to undo numbers that have been squared. So for example, the square root of x squared equals x. And here's that same example I used before. The square root of 81 is 9. This can be read as the root of 81 or radical 81, or I always say square root of 81. And then this is really important. Notice there is no index. We always assume if there is no index that we're doing a square root. Next, we can say cubed root. So now you can see the index is 3. That's why I'm reading it as cubed root. Used to undo numbers that have been cubed. And so here's our property. Cube root of x cubed is x. Notice it cancels out. And then here's an example, the cube root of 27. So we have to think about what number times itself 3 times, and I picked 3 times because of the index, will give me 27. And we just did that one up here. That one's going to be 3. Okay, and then lastly, all we're going to talk about in Algebra 1 in terms of the radicals will go up to 4th root. Notice my index is a 4, used to undo numbers that have been raised to the 4th power. And then here's our property. The 4th root of x to the 4th is x. And then let's check out this example. We use that index to tell us what number multiplied by itself how many times. So the index is a 4. I need to come up with a number that you multiply by itself 4 times to give me this base number 16. And we just go through trial and error if you're really not sure. Well, 1 times 1 times 1 times 1 is 1. Doesn't work. Let's try 2 times 2 times 2 times 2. Hey, that does give me 16. So I know the 4th root of 16 is 2. Let's practice some more of those guys. So if we go on to page 3, find the exact value of the nth root. So I see a is the cube root of 8. In my head, I'm thinking about what number times itself 3 times, because that index gives me 8. Another way you can think about it is by doing a factor tree. Okay, so we're going to do those 2 little tree branches, and I'm going to come up with numbers that multiply to 8. Well, numbers that multiply to 8, that's 4 and 2. And then if I break down anything that's not prime, so 2 is prime, we're going to leave it where it is. 4, I can break down to 2 and 2. As soon as I find 3 of a number, that's telling me my answer. So I found 3 2s, that's telling me the cubed root of 8 is 2. And now let's check another one. The 4th root of 81. let's do our factor tree. So numbers that multiply to 81, well, I know it's 9 times 9. 9 isn't prime. I can keep breaking it down. 3 and 3, 3 and 3. I'm looking for fours of a number, right? There's a number that happens 4 times, and that's a 3. So my answer is the fourth root of 81 is 3. We can do the same thing with negative base numbers. So I've got the cube root of negative 125. Let's break down with a factor tree. I've got 5 and 25. 5 times 25 gives me 125. I can break down 25, and I'm looking for 3's of some number, and I've got 3 5's here, so my answer is 5. And it's going to be a negative 5 because my base is 5. And so let's make a note about that. When the base number is negative and the index is odd, then the solution is negative. Okay, good job, guys. One last thing we're going to talk about in this video is estimating square roots. So if we know we've got perfect squares, so for example, square root of 16 is 4, square root of 25 is 5, well then what is the square root of 20, right? We know our perfect squares, but we can use a number line to help us estimate the square root of non-perfect squares. So let's check out estimating the square root of 20 as a rational number. So if we break down 20 using a factor tree again, 4 and 5, 2 and 2, we can think about, well, 4 is the square root of 16, 5 would be the square root of 25. And we want to find what's going to be in between there to get the square root of 20. So I know that it's going to be a number between 4 and 5, right? Because 4 gives me the square root of 16, 5 gives me the square root of 25. So we can say maybe about 4.5 is going to be the square root of 20, because 20 is between 16 and 25. So let's check out another one. Estimate square root of 72 as a rational number. So if I go to break down 72, I think about 9 and 8. And then I want to think about those square roots. So 8 would be the square root of 64. 9 would be the square root of 81. 72, and we can use our number line. We can say if this is 8 and this is 9, and this would be the square root of 64, and this would be the square root of 81, the square root of 72 is going to be in the middle. So we can say the square root of 72 is about 8.5. And then let's check out one more here, estimating the square root of 125 as a rational number. Let's break down 125. I can break down 125 with a, let's see, 11. Well, let's just try 11 is the square root of 121, and 12 is the square root of 144. And so the square root of 125, see how it's in between? 125 is in between 121 and 144. It's closer to that 121, so I could say maybe it's about 11.2 is the square root of 125. Okay, so this, guys, is just a little refresher on square roots to start our chapter 6. And we are going to keep practicing and keep learning more new concepts about square roots. Great job, guys. Don't forget to submit a picture of your notes.